So I want to start talking about the different types of errors. I want to start by saying that when we talk about types of errors that we make in a test, the error of a test has nothing to do with the person conducting a test, okay? But when you think about, like, as we're using p hat to test a claim about p, that p hat comes from a sample. And what do we know about samples? They're not perfect. So as we talk about these errors, I want you guys to understand that, one, they don't happen frequently, and two, if someone makes a type 1 error, it's not the individual making a type 1 error. Instead, it's like the sample results in a type 1 error. Did you catch my drift there? Okay. And to kind of take you through this, to understand that there's two different ways we can kind of make mistakes, I want to talk about the criminal justice system and hypotheses. So guys, if someone has been accused of a crime and they have to go to trial, what's the underlying principle of somebody when they go to a trial? That they're innocent, and with enough evidence, if the prosecutor comes in, they give enough evidence, we reject their innocence and conclude guilt. Is everybody with me? So in some respect, my null hypothesis, what we assume is that somebody's innocent, and then with enough evidence, we reject that innocence and conclude our alternative hypothesis of guilty. So let's go ahead and say that unbeknownst to the jury, we happen to know that the person is innocent. And if that person is innocent, we can still come to two different verdicts. Either we find innocent or find not guilty, and if a person goes to trial and they're actually innocent, and we find them not guilty, aren't we making the correct decision? If they are actually innocent, right? Now, what if we find them guilty? What would happen? Okay, but overall, that conclusion is? It's an error of some kind, yes? And the overall consequence to that error would be sending an innocent to jail. And both of those are if that null hypothesis is true. Okay? So one type of error a test can make is if the null hypothesis is true, rejecting the null, and we call that one a type 1 error. Yeah.
What's that top word say next to found not guilty?
Correct decision. It's 2 words. You can't tell? I screwed up. And then rather than hit erase, I just tried to hide my screw up. Okay, what's the other possible truth besides the person is innocent? They're actually guilty. And if they're actually guilty, but we find them not guilty, are you guys with me that would also be an error? And the consequence of that error would be letting a guilty person go free. So are you guys with me that sending an innocent to jail and letting a guilty person go free are both mistakes, But they're two very different mistakes. Are we comfortable with this idea? Okay, so we call this one type 2. Now, what if somebody's guilty and we find them guilty? That's the correct decision. And when we set up a test, our hope is that we get one of these two boxes, right? But we have a sample. Samples aren't perfect. So sometimes we get one of those wacky samples, even though we grab it randomly, we do everything right, it's still a wacky sample that makes us make the wrong decision, and that's possible. Okay, so in my experience, kids are very good at describing the different types of errors, but sometimes they forget which one is which, okay? So a type 1 error, the null is true, and we conclude HA is true. And so one of the things that in the past that has helped students remember this, okay, is that for type 1, the hypothesis we write first is the true hypothesis. That's just a way to remember which one's which. Okay, for type 2, HA is true. But we fail to conclude that HA is true. Because we never really conclude that HA is true, or the null is true. And again, in this case, type 2, the second of the two hypotheses that we write is the true hypothesis. And, I'm sorry?
Wait, you say that the alternative is true, but we fail to conclude that it's true.
Yeah, because we're making a mistake, right? We're describing an error in decision making, yeah? All right, and just for fun, I got one quick thing to show you. Just one more visual to help you see. Type 1 error. Obviously, this person with a mustache, not pregnant, right? So this would be, we assume not pregnant and conclude, with enough evidence, conclude pregnancy, yes? I just think this one's kind of funny. And this woman, very obviously pregnant because nobody in their right mind would let somebody just put their hand on their stomach like that, right? Unless they were pregnant. That would creep me out if my doctor did that, right? Everybody good? Is this a fun visual to kind of remember this? I think it is. Everybody good? All right. A question like this, right? If they give you the full, like what was just on your quiz, all you'll have to do is the first half of it. Or it is this question, okay? They're not going to have a free response question that includes, is this convincing evidence where you're supposed to do the full test, and then ask you about errors in alpha, okay? So there's two components of dealing with these type 1 and type 2 error. What you're going to need to be able to describe an error in context, okay? And then the second component of what we're going to ask you guys to do is going to look terrible while we do it, but I promise we'll circle back around and tell you what you actually need to know. We're going to do some pretty annoying calculations that are going to feel very there's no way I'll remember to do these calculations. And I've got great news, you won't have to. You'll just have to understand the underlying concepts. But I'll circle back around, I promise. But first, you guys remember this example where we said Mrs. Turner claims she beats Richard 75% of the time? But in reality, come on. But in reality, we think she's overstating her abilities. You guys remember this? And let's go ahead and pretend we haven't run this test. We don't have our sample. Okay, so usually this error analysis would happen before we run the test. Okay, so you guys, let's describe a type 1 error in context for this particular setting. So which hypothesis is true for a type 1 error? The null, because it's written first, right? That's why okay? So the error would be Mrs. Turner actually beats Mr. Richards 75% of the time. But so that's what's true. And if we're describing an error, what are we going to conclude? But we conclude she's overstating her abilities. That she's now, one of the things, and this will take a second for us to get to, okay? The reason we do this is we want to think through the consequences of each type of error, okay? What would be a consequence if we ran this test and we concluded that Lombardi or Turner is overstating her abilities? What would we do?
Tell her she's cocky.
Huh?
Tell her she's cocky.
Yeah, in fact, you know what we might do is falsely accuse her of lying. Everybody good? All right. What would the type 2 error be?
If she does beat him less than 75% of the time, we include that she does beat him more than 75% of the time.
Okay, hold on. We never conclude the null, right? Okay, so the type 2 error is always really funky to word, okay? So let's go ahead and say Mrs. Turner is actually overstating her abilities. But we fail to reach that conclusion. What about a consequence of that? What would that consequence be?
Unworthy praise.
Unworthy praise? She continues to think too highly of herself? You guys, yesterday during 8th period, or Tuesday during 8th period, she walked in right as I was going over this example. It was pretty funny. All right, you guys. Which one, in your guys' opinion, which type of error is more serious? probably type 1. You guys are students. Falsely accusing a teacher of lying will not bode well for you. Letting them continue to think too highly of themselves is just fine. Shockingly, in my perspective, I would go the exact opposite, but that's just because I like humbling people sometimes. Everybody good? All right, so if a type 1 error is more serious, maybe one of the things we want to think through is how can we minimize the probability of us making a type 1 error? Does this make sense? Okay, so this next part that I'm going to take you through is where we're going to have these like really tedious, minute calculations that are going to feel impossible. I don't expect you to make any of these calculations. I want to show you where they come from. And at the end, we're going to circle back around in terms of like what is the big concept of what I'm about to talk about. Okay, so we kind of have two possible truths here. Regardless of what our test comes to conclude, we either have that the null hypothesis is true or that the alternative hypothesis is true. So as we kind of think this through, we have all these possible p hats, right? And let's go ahead and think about this if H0 is true. Now, that would mean, by the way, that P is equal to 0.75. So we're going to have this normal distribution because we have a huge sample, a big enough sample size for sure. All right, and we're thinking about those possible P hats. And can you guys help me out? What would the center of the P hats be if the null hypothesis is true? 0.75. And the standard deviation would be, I'm going to need some help with this, the square root of 0.75, 0.25 over 100. Because our sample size for this example was 100. .04? Okay. Can somebody remind me what makes us reject the null hypothesis?
It's less than 0.05.
If what is less than 0.05? The probability from the z-score, right? Which is essentially if our sample is really unlikely. Is everybody with me? So is it possible that we could, when we get our sample, get this be true, but we still get one of the unlikely samples? And where are those unlikely samples in this example? On the left or on the right? On the left, because we would conclude P is less than. Okay? So for instance, if I got my P hat from, say, here, even though that's it's possible, I'd make the wrong decision. Is everybody with me? All right, so I'm going to go ahead and look at this 0.05. I'm going to call this region 0.05. And this is going to feel like trivial, but it's not. Are you guys with me that if I get a p hat to the right, that this area for this p hat will be bigger than 0.05? Okay? And if I get a p hat to the left of that line, that one's going to have a p-value of less than 0.05. Is everybody, we good? All right. Now, if the null hypothesis is true, so this black area here is essentially where I'm going to reject the null hypothesis. Is everybody with me? All right. And this unshaded area is where I'm going to fail to reject the null hypothesis. What is the right decision on this graph where the null hypothesis is what is true? Should I reject or fail to reject if the null is true? Fail. If the null is true, we don't want to conclude that it's false, right? Okay, so this blue area is the correct decision. What's that black area? It's a mistake, yeah? What kind of mistake?
The big one.
Which type of error is it?
Type of type.
That would be a type 1. And according to this graph, y'all, what's the probability we make a type 1? Why 5%? Because that's what we set alpha at. And if alpha was 10%? If alpha was 10%, what would my probability of a type 1 error be? 10%. So, the probability of a type 1 error is equal to whatever my significance level is. So, given that we said a type 1 error is more serious, do you think maybe we should, man,
Couldn't you minimize it by making alpha small?
so lowering alpha lowers the risk of a type 1. Awesome.
But doesn't that also make the data like, because if it says 0.25, then it could be a small number and it's still like set.
Say that again.
Like it could be a small, it could be like 0.025, but then like that makes the null like have such a wider amount of numbers. I don't know if that's makes sense.
I'm really not understanding what you're trying to say.
Come back.
Come back to it? Okay. Easy peasy, right? We just lower alpha. Cool? Perhaps there's some nuance that we have to be careful about. Is that okay? Are you guys with me that since I know that error is 0.05, right? I know the mean, I know the standard deviation. There's actually a cutoff value for p hat that's going to tell me when I'm going to reject versus not reject. Is everybody with me? And if I ask you to find this, if I have the area, the mean, and the standard deviation, isn't that a pretty quick thing to find? How do I do it? Inverse norm. Jackson, have you already started punching it in?
.684, so 60 out of 100 games.
We'll leave it as 0.684. That's fine. Okay. Are you guys with me that what that basically means is this test is going to reject when we get a p hat that is less than 0.684. Are we comfortable with that idea? And these hypotheses, all this stuff is set in advance, regardless of what is actually true. This test is going to reject whenever we get any p hat that is less than 0.684. Okay? So now, let's go ahead and pretend, and you guys, I changed this example to make it more relevant. And so we're going to erase that part because I didn't change it all the way through. I just screwed up. Okay? So I want you, let's go and say, well, what if Turner really beats Richards 65% of the time? what would those p hats look like? First of all, if this is the actual truth, if this is the actual truth, what decision should our test make? What's the correct decision? The alternative is true, so the correct decision would be reject H0. Is that, you guys with me? And if I don't reject H0, I'm making an error. But what kind of error is that?
Type 2.
It'd be type 2. But now what would, so this is HA is true. My mean would be 0.65 instead. Okay. Well, when my standard deviation is going to be the square root of 0.65, 0.35, all over 100.
Point zero four.
0.04. Thank you. Everybody good? And you guys, when are we going to reject the null hypothesis? We've already figured that out. Is everybody with me? Okay, so if we're going to reject when we get a p hat less than 0.684, we found it up here. When we did that inverse norm. Because remember, the test is going to assume, the test always assumes you're on that null hypothesis is true graph. That's what we do. We assume the null is true. So the cutoff value for when you're going to reject or fail to reject is the same either way. No matter what. All right, so you guys, and now again on the graph, this is that correct decision. This is a type 2 error. So if I ask you guys, what is the probability we get the correct decision given that the actual p is 0.65? To just review some of that. Could we figure that out?
Sure.
It's a normal CDF question, yeah? What are we getting? 0.76? And we call that number, it's got a specific term. We call that the power, okay? It is the power to detect p equals 0.65. The power of this specific test with this null hypothesis to detect if p is actually 0.65. Okay? You guys, if that's the case, what is the probability of a type 2 error? when you think about it, isn't a type 2 error that you reject given that the alternative is true, that P is equal to 0.65? You guys with me? So it would be 1 minus that 0.76. So when we talk about this idea of what we call this power, which is an extremely abstract concept, okay? Power is the probability you make the right decision when the alternative is true. Type 2 is the probability you make the wrong decision when the alternative is true. Okay? So the power plus the type 2 error will always equal 1. Because they're basically the two different decisions you could make when the alternative hypothesis is true. Now, we got one more thing I want to go back and talk about. We said lowering alpha lowers the risk of a type 2 error. So guys, what would happen to this graph if I lowered alpha? If I didn't use 5%, let's say I used 1%, what would happen?
When you get more type 2.
Well, let's not make that's a pretty big jump. So what would happen to that top graph? Instead of my cutoff being 0.684, it's gonna move way over, right? So let's go ahead and use that purple area. It would be 0.01. And that's going to change that cutoff value. It won't be 0.684 anymore, will it? It's going to be further over, like here. So lowering alpha does lower the risk of a type 1. Unfortunately, it increases risk of type 2. So hear me out. If this is my probability of a type 1 and type 2. As I lower the probability of type 1, my probability of type 2 is going to go up. If I raise my probability of type 1, my probability of type 2 is going to go down. Because as I change alpha, I'm changing my probability of rejecting. Which if I'm more likely to reject, I'm more likely to make a type 1 error and less likely to make a type 2. Because they're opposite decisions. Is everybody with me? You make a type 1 error when you reject, and you make a type 2 error when you fail to reject. Depending on what is true. So remember how we kind of said which one is more serious? If a type 1 error is more serious, that would make us want to have a lower alpha. If a type 2 error is more serious, we might be more willing to, if we're more willing to make a type 1 than type 2, we might use a higher alpha. So, in terms of which alpha should you use, if it's not given to you, go ahead and use alpha equals 0.05. Okay? And the College Board will not expect you to set alpha based on these errors. Okay? They won't expect you to go through this whole process. Okay? But what they might say is explain they might have you do the error analysis and say, explain which alpha you would use. But they won't expect you to do that on idea is recognizing the idea that they work against each other. Power and type 2 are complements of each other because they both happen when the alternative is true. One's a good decision, one's the bad decision. Okay? So in terms of all these little calculations, you won't have to do anything. You won't have these types of calculations in a typical free response question. The coming up with this number and this number and this number and all that kind of stuff, it's not going to happen. You won't have to calculate power. But you will have to understand that how power influences the probability of type 1 and type 2. And how alpha influences type 1 and type 2. Everybody good? And that is a good place for me to stop today.